Okay. Hmm. Okay. I know if you guys can hear me. Probably can. I know I can make OBS show me comments. Let's quickly do that here. OBS comments. Live stream comments.
In this video, I'm gonna show you how to overlay your comments while live streaming on YouTube
I
Live.
need to overlay them. I just I know. Probably need to find it in the Windows to check docs. Live chat. YouTube chat. Yeah. If anyone's here, could you send a chat message and I'll probably see something. I'm just gonna jump on the link and test chat so that we can see. Oh. Cool. It's just weird being alone and talking to myself in my office and then going like, yeah, one watching on, that's good. Viewers 1, likes 0. Can I chat? It's like I haven't. Oh, nice, cool. Someone did a thing and said nice, awesome, memes, nice, cool. Chat swag. Uh, Excuse me, I might have someone at the door. Oh, sorry. Yeah, thank you. Is it it? Is that it? Okay. Okay. Thank you. Is that it? Have a nice day. Okay, cool. Seems like we have comments. They're working, and if you need to ask any questions, please feel free to do so in the chat. Let's go. Who's that? Who's that, Drickus? So today we're going to cover STM32. I do have an STM. Do I have another blue pill? I do have an STM32 here. It's a blue pill, and this is kind of like, how do I say it? It's a entry level microcontroller that you can basically start out with if you don't want to. Not if you don't want to. It's a good one. You can start out with this and use it as you need. So what I'm going to do today is try and do the first part of the series where we build out SPI drivers. So SPI complete SPI drivers all the way from scratch for the Bluepill, which is the STM32 108, STM32F1 F1xx series. So it could be a 108. I think there's a 106 and something else of the sort. So the first thing we're gonna do, the first thing we're gonna do today is kind of walk through the, how do we call it? We're going to walk through the functional description, and then after we walk through the functional description, we're going to now come back and build, I think, the beginning structs, and maybe just the structs, but maybe we do the structs and the clock control for what do we call it? Structs and clock control for SPI on the STM32F1xx series. I'm gonna close it. STM32F1xx series. So I'm gonna get my stuff ready, and just getting all my stuff ready, and then we'll go from there. So, and I think I need to open. If I'm not wrong, I need to get the reference manual for the STM32. Yeah, cool. Uh, if is this too small to see? Can everyone see? Any sort of questions? Cool. Thanks for the comment test. Is that it? Yeah, okay, cool. So that works, and we're pushing out. So the first thing we need is in order to set up STM32 SPI, the documents you're going to need. Number one is the Bluepill reference, the STM32F1 series reference manual. So that's this document, overview of the manual, or an introduction into the manual. Is this? Yeah, kind of. This is the reference manual for the STM32F1 series. You can get this at so if you go to STM32F1xx F1, that's fine. There's 103 F1 reference manual. This should probably be there on provision from ST. Yeah, it's the same manual we have, as you can see. Yep, STM32, F102, F103, F105, and that is the exact document we have here. RM, I saw like a watermark. Yeah, RM008. So that's the first document you're going to need, and then the other document you're going to need is STM32F1 datasheet. You're gonna need this later when you kind of like building out the buses. It's just a datasheet, and then since the STM32 runs on Cortex M3, Cortex M3, you're gonna need a Cortex M3 generic user guide. Yeah, you're going to need the Cortex M3 generic user guide so that you can kind of figure out interrupts and where the addresses are for the interrupts, and what else? We'll, as we go along, we'll find out why we need all of these documents, and then we can go over them for that. Okay, cool. So let's quickly talk through the what do I say? What do I call this? Let's quickly talk through SPI for SPI on STM32 F1. So what is SPI? If anyone does not know, SPI is a serial peripheral interface. Is I think that is that's I'm just gonna open the either the wiki documents or everything. So it's a serial communications protocol or standard, and it's primarily used in embedded systems, and it's mostly used for shorter distances but higher bandwidth. So it's pretty fast compared to say something like I squared C or or UART or something. But then the thing about SPI is you can't really go, I think, over 10 foot in distance. Like the distance is quite short, so you can't really use. So if you had like two chips in your car that needed to talk, you would need something other than SPI because your car would be more than 2 feet apart. So you kind of want to use it on small boards that are very connected and uh, quite used. Okay, cool. So we understand what SPI is. And if anyone has any questions, please feel free to like leave them on the chat. I'm super like I'm willing to answer any questions, and also they'll reveal things that I don't know myself, which is kind of what I need. Okay, cool. So SPI, serial data communication between a master and a slave, or a main and a subscriber, or a server and a client. We don't Master and slave is the kind of the word that's used, and all the documents are going to use master and slave. But I mean, we live in a politically correct world, and you want to say master, you want to say main, subscriber, server, client, or something of the sort to avoid the slave moniker. But then at some points, I will say that, and it's just that's the documentation, that's the words that they use. There would be. Cool. So step one, we know what serial communication is. I think so. So yeah, we can probably find out what serial communication protocol. I hope this is not a protocol. But yeah, I was hoping for this rather not to find out there's a serial communication protocol. But so serial transmission, as the name implies, serial data sends one bit at a time with the bits sent over the same conductor. Basically, it's like one and then two and then three and then four and then five and then six. And with parallel communication, you could have like it could go like one, five, and seven, seven, eight, and nine. It could be. So the serial communication is one at a time, and it kind of like it works for higher throughput. If I would say, I'm just reading now my screen and stuff. Cool. We know what serial communication is. Okay, in when so as we start this, we're going to look at the reference manual of the Bluepill. And in the reference manual, if you go towards, I think, around chapter 25, we will find out about the serial peripheral interface. This is where kind of like the whole description of what SPI and how it works on the Bluepill is kind of in here. From here, basically all the formulas that you need to use for communication are here. And oh, applications of serial. So this is I'm seeing a question. Applications of the technology. You can use serial technology for. I think we had a document just now that was showing us. So applications. Let's look at applications. Yeah. Uh, so something that needs high throughput that doesn't need a very long distance, that doesn't cover a very long distance. So think about something like how do I say this? Something like you have two devices uh, in in you have two devices in how would I say it? You have two devices in a close proximity, and they need to send data at quite a high they need to send each other data at quite a high rate, and the distance between these two devices is oh wait, what? Why are we on that screen? Hmm, that doesn't make sense. No, left and right. Okay, and then I need to do this. Shame. Yo, I've been on the wrong screen all this time. I didn't even know. I've been opening documents and oh my word, my fast stream. Don't worry, I'll get better at this. I have a tendency of learning things and getting better at them. I'm now resizing the screen so we can see everything that I'm reading in a better way. Can I do the opposite? And then I'll move it, something like that. Okay, cool. Sorry about that. Um, Memes, especially because you were here and I've been speaking to you. Cool. I've been on the wrong screen. Now I'm on the right screen. It's fine. Um, Applications of serial technology. You wanna use it where the distance between the communicating devices is not too long, and then you also wanna use it where you need higher bandwidth of like you wanna send data at quite high bandwidth. The speeds for serial communication are higher due to like synchronized, like there's less overhead because there's a shared clock. We know how fast it's easier to send 1 bit at a time. Cool. So cool. So let's go back to SPI productivity here. I think I wanna maybe hide sidebar so that we can see more, and then I kind of wanna compress this a little bit so we can see all the way to the other side of the page. So cool. And then maybe I'll make myself a little. Oh, I thought I could make myself a little bit smaller. Pardon me, I'm still learning how to stream. This is quite hard for me. Cool. SPI. So, um, this is all an introduction of the SPI in STM32 applications shares pins with shares pins with some applications, with some other protocols. Well, yeah, what other protocols? The JTAG, JTDI, and I2S. JTAG is a debugging protocol. I'm not going to go over it now. It's a way. We'll get to it. We'll talk about it later. Um, I2S is, if I recall correctly, it's audio protocol. Yes. I2S is I squared S, I2S. I don't know. Is it I squared S, I2S? But I2S is a audio protocol. So basically, you use this to like send audio between microcontrollers. Um, good. So those pins are shared, and when you're going through kind of like when you're doing a development for whatever board you're working on, you need to know which pins are shared, which pins can do what, and what do you need to enable or disable to talk about those pins. So let's look at SPI's features here. So number one, we have full full duplex synchronous. So full duplex synchronized sending. So this one is sending or that one is sending, not at the same time. So that's synchronous. And then we've got simplex synchronous transfers on two lines, with or without bidirectional data lines. So you can have two lines, and then you can have a simplex mode, which is either either the subscriber is talking or the main or master is talking. And then when using SPI, you can choose between 8 or 16-bit transfer data from data formats. You can choose between master or slave operation, or better, a main and a subscriber operation, or a server and a client operation. You can have multi-master mode, which is where you have many. So you have one peripheral, and you have a lot of controllers that can control that very one peripheral, and they, your peripheral is allowed to have many, to collect from many controllers, let's say. And then you can set a baud rate, which is the prescaler for the clock. Data on SPI is limited to travel as fast as the clock pulses. So you can set how fast the clock pulses using the baud rate prescaler. A prescaler is basically a divider. So you show up with 100% of speed, and then there's dividers that let you have like 100 divided by 2 divided by 4 divided by 5, 24, all the way to as I think 16, if I recall correctly. Um, you have slave mode frequency, so you can choose your frequency from the slave side or from the subscriber side. You have faster communication for both master and slave. You have NSS. I forget the full name of this, but this is a select pin basically. The slave management select pin. You can either use actual pins to control which chip you're talking to at a time, or you can end up using software to control which chip you're talking about. And this is like, if we're thinking about, like, say you only had one chip and you wanted to talk to this chip over SPI, and then you don't need to add another like physical line to speak to this chip. You can just set it that you always know you're always going to have one chip. You can set it so you're talking to that chip all the time, and you can use the other GPIO pin or line to do something else. Say you have very limited pins and you're on a very small microcontroller. Uh, Programmable clock polarity and phase. So we'll get to there. But clock polarity and clock phase is what SPI uses to determine when to start reading or writing data. So if you set it, it could either start at the leading edge or trailing edge of the clock. And if you the phasing also, you could set it so your clock is always off when you're not talking, or you can set it so your clock is always high or on when you're not talking. So that is clock polarity and phase control. So something of so. Programmable data order, you can start with most significant bit. So when you're sending data over SPI, you're sending data in bits. So yeah, yeah. So if you're sending data over SPI and you're sending, crap, I opened a new tab instead of zooming super in on that. What I want to show is this. So this is the most significant bit. This is the least significant bit. We know this. This is basically math class. I think basic numbers or something, class 1 or class 2. I don't remember. So this is the least significant bit, and this is the most significant bit, and this is the least significant bit. When it says we have programmable programmable ways of sending bits, it means that we can choose whether we're starting with the most significant bit or least significant bit. That's when we're shifting through the registers, which is something I'll touch as we go along. Okay, we have transmission and reception flags that have interrupts. So you have interrupts to tell you whether transmission has been finished or reception has been finished. So that way you can kind of move to the next. Um, you can move to the next thing, or you can set the next message or something. And then we have a busy flag, which you can use to check whether is SPI being used. So you can't do something, or you have to wait for something. And then we have hardware checksum stuff, which is for like making sure the data you sent is kind of confirmed and is sent properly. And obviously, as you can see, we have automatic error checking and checking of the last received bytes. Uh, we have master mode fault, which is something we use when two masters speak at the same time and then there's a conflict. So that's kind of like for conflict resolution in systems where there's multiple masters. We can use DMA. We're not going to use that this time. That's going to be in an advanced thing. But direct memory access is basically where we escape the shift registers, which I will explain what they are. Basically, the way SPI works is there's a shift register on each side. This little register, it says shift register, shift register. And the way it works is, can I do some notes? Some notes here. Can I do some notes? Probably can do notes here. Note, and I can drag this here. So this is the way the shift registers work in SPI. So let's say this is the master side. The master side is the left and the slave side is on the right. And you're sending data, say, from the master to the slave. And you have B7, B6, B5, B4, B4, B3, B2, 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 B1. So these are 8 bits that we have. And you want to send these bits to a register that is, say, garbage 1, garbage 8, garbage 7, garbage 6, garbage 5, garbage 4, garbage 3, garbage 2, garbage 1. And the way shift registers work in serial communication is we basically send serial communication. We send one bit at a time. So the way shift registers work is these two shift registers are connected, and you don't need to worry about it. This is actually done at the electronic layer. So, but knowing how it works is beneficial. So when the clock pulses once, each clock pulse, the data is one bit is gonna be sent over, or one bit is gonna be shifted. So it's gonna look like this. It's gonna look like G1, B7, B6, B Can I zoom in? Can I zoom in here? Can I really zoom in? Make this like, what can I do about this? Title? Just always use title. Okay, so it's gonna B7, B7, B6, B5, B4, B3, B2. That's it. And then we're gonna go there, and then it's gonna be B1. This is actually okay, that's fine. B1 all the way, B7 to B1 to B0. Because we want 8, no? So B1 and then G7, it could be G8 to G1, so that's fine. So this is G1. So and then the other side would look like it would shift. So this would be B0, G8, G7, G6, G5, G4, G2, G3, G3, G2. Okay. And then the next one would go like G2, G1, B7, B6, B5, B4, B3, B2. And then on the other side, it would be B1, B1, B0, G8, G7, G6, G5, G4, G3. Okay, G2 is on that side. And eventually what we're going to have is on this side, on the standing side, we'd have G8, G7, G6, G5, G4, G3, G2, G1. And on the other side, this is at the end with after 8 clock cycles, basically. We would have B7, B6, B5, B4, B3, B2, B2, B1, B0. Okay, cool. So this is after every time, this is clock cycle, okay? Clock cycle, clock cycle, clock cycle. So, and so on and so on and so on, and then until we're done. So as you can see what's happening, I'm just going to check what's up to see if anyone else is talking or asking questions. Cool. So basically every clock cycle, we're going to shift one data bit, and one data bit is going to go from one shift register to the other shift register. That's how shift registers work. Okay, cool. So we were exploring that, and when you're using direct memory access, you're not moving data one bit at a time. You're reading like a word, which is a group of bits from the master side from directly from memory access on that side, and you're reading that data from that side and transferring it directly to say the slave side directly to memory on this side. So you're kind of avoiding all the shift stuff and all the stuff, but this is more advanced and it's faster. We don't have to deal with it at the moment, and we can understand SPI with that. Cool. So let's go to the next thing. So I squared C, we're not going to cover this. This is a transmitter or receiver of audio, and we can use it for audio. We're not doing audio right now. So you can look at this is a block diagram of SPI, and this is on one side. Basically, we have a read buffer, and we have a write buffer, and then we have a shift register that we talked about. So this shift register is on one of the devices, so either the master or the slave. And then obviously you have a few registers. You have an SPI control 2, SPI status register, SPI control 1 register, where you can set up stuff. So say like in the control 1 register, you have LSB. You can set whether to set LSB or MSB fast. You can check whether there's an SPI error. You can check there's master settings, there's polarity and phase settings, there's modes to set whether you're bidirectional mode or single mode, and enabling CRC, and then you have data frame format, and then you have slave select management, and then slave select itself that you can use on the control 1, and then on control 2 you have register for this is transfer, interrupt, um, uh, receive interrupt, error interrupt. I think this is reserved, and then SSOE. I know we use that for either. I think we use that for interrupts or something. We'll get there. I'm not. I don't remember everything. And then this is, I think, to enable or disable transfer, and then you, you have a status register saying whether it's busy, over, mode F, that's I think a master error, CFC error, or transaction error, or receive error. Now, when using SPI to communicate between two devices, you basically have to connect 4 pins. There's a MOSI pin, which is a master out, slave in. So master sends data out, and the slave reads data in through this pin. And each side of the communication protocol in SPI is going to have the same pins. So there's going to be a MOSI on master and slave. And then we have a MISO, which is master in, slave out. Master in and slave out basically is for the slave to send data to the master, and for the master to read in data. Okay. And then there's a SCK or SCLK, which is source clock, which is the source clock is the clock that is used to synchronize the sending of the data. You remember when we talked about how data is sent in SPI, basically every clock cycle we shift over a bit. So the master in SPI, the master must always provide the clock, but I think there's a way we can set it so we can use an external clock. But that external clock if we end up using an external clock, it will almost end up looking like it's coming from the master side. So basically the master is the one that's supposed to provide a clock. And then the other pin that we need is the NSS pin. The NSS pin is basically, it's a slave select pin. We use this pin when we want to choose which slave we want to talk to and how we want to talk to that slave. Cool. That's kind of it with the pins. Yeah. So quick recap. Yeah. Master in, slave out. This pin can be used to transmit data in slave mode and receive data in master mode. Master out, slave in data. This pin can be used to transmit data in master mode and receive data in slave mode. Cool. SCK or SCLK, you'll find this in other documents. This might be labeled SCLK. A serial clock output for SPI masters and input for SPI slaves. Cool. So clock is coming from the master. NSS, slave select. This is an optional pin to select a slave device in case you have a multi-slave environment or even a multi-master environment. And this pin acts as chip select to let SPI communicate with slaves individually and obviously avoid any conflict of data between the slaves or masters. Cool. Awesome. There's some operational environment here that we see. Here we can see this is an optional pin to select a slave. This pin acts as a chip select to let the SPI master communicate with the slaves individually and to avoid contention on the data lines. Okay, cool. The slave NSS inputs can be driven by a standard I/O port, so you can actually use just a pin, a GPIO pin, to drive the slave when the NSS pin may also be used as an output if enabled. basically as SSOE bit by the SSOE bit. We'll get to that. And driven low if the SPI is in master configuration. So you can kind of move from master to slave mode using the NSS pin. Okay. But you'll have to add a few more bits. We'll get to that. So if the SPI is in master configuration, the NSS pin may also be used as an output if enabled using SSOE bit and driven low if the SPI is in master configuration. In this manner, all NSS pins from devices connected to the master NSS pins see a low level and become slaves when they're configured in NSS hardware mode. So basically you can basically have equal devices that decide when they're master or they're slave, and they can kind of help each other. So when configured in master mode with NSS configured as input, master 1 and SSOE 0, and if NSS is pulled low, the SPI enters master mode fault state. The master bit is automatically cleared and the device is configured in slave mode. So basically you can use this pin to swap between master and slave modes, if that makes any sense. Questions on WhatsApp or on YouTube? Not a worry. I'm gonna give you guys a few minutes. Any questions? Any questions? As I set myself up now. Okay, cool. Awesome. So let's go Steam here. Cool. What's the next thing we want to do? So the next thing we want to do is look at as we were just talking about right now. So quickly, there's a few diagrams here. Single master, single slave application. Master in, slave out, master in, slave out. So this is a master, this is a slave. The slave is on the right, master is on the left. And there's a shift register, there's a shift register here. Cool. Mosi. So master out, slave in, master out, slave in. You basically connect the same wires. Okay. And you can see SPI clock generator on the master side. Goes to a SLC, SCK, and SCK. And then there's an SSS pin on the master side that is not used if SSS is on the slave side. It's not used if SSS is managed by the software. Okay, cool. So let's first look at how we can do bus configuration. Okay, cool. So this is now we're getting to how to configure SPI. So there's a minimal way you can configure SPI. If you have one master and one slave, you might actually need just two pins. Number one, you don't need the NSS pins because you can just drive the NSS pin to ground from the slave side. Okay, so basically short it to ground, and that slave is always going to be active. And if you have one master, one slave, it's not a problem. And then master of Mosi to master of slave, and then clock of master to clock of slave. So basically, you need two wires only for that. And this is considering you can have you can set it so if you remember how the registers work, inevitably you have bidirectional transfer of information because regardless of what happens, you will send data from the slave to the master, even if you're writing from the master to the slave. The shift register will still absorb some data. So basically, you see where G7 goes and B7 comes. So the minimal setup of SPI, you have two lines, two pins connected, which is the Mosi of the master to the mercy of the slave, which is master out, slave in, master out, slave in, and then the clock from the master to the clock to the slave, and then all the other pins can be used for something else. So if you're limited with pins and you want to do something else and you only have one SPI peripheral in your system, you can't end up doing it in such a way that you only use two wires. That's the most minimal configuration of that we need. But the rest of the time, so we will use. This is the things we need to set up. So we need to, when using SPI, one of the first things we need to do is, if you think about, there's a master and there's a slave. So number one, when you, let's assume it's a general world and we don't know how many slaves there are. What you need to do is, from the master side, you need to decide which slave you're speaking to, and then choose that slave and then start speaking to them. So let's look at how slave select is done. So we have two modes of slave select. You can have either hardware slave select, which is where you actually use hardware. You use the hardware NSS pin. We had a diagram for this just now. We had a diagram. Yeah, so you use the pin itself, and you power it high when you're not using it, and then you pull it low when you're using it. So inside our registers that we looked at before, there was this registers here, there was this register, there was this diagram that showed us registers. This registers. There's what is it? SPICR1 has SSM bit. And if we set the SSM bit to 1, we are choosing to manage slave management using software. So basically, if we set this bit to 1, SSM in CR1, this one, we're saying we will use software to manage the bit, the slave selection. And then we can drive it internally by the SSI bit. The SSI bit is now the bit. So SSM says, hey, we're using software to manage the pins. Okay, cool. SSI is the one now we control with the software. Okay, so SSI is like software, SSM is software mode, and then SSI bit, we use it to actually say, now activate as a master. Okay. And then there's hardware slave management, which is the kind of normal one we expect, not the code one. In hardware slave, SSM is 0, so we're not using software. And then NSS is enabled. NSS output is enabled, which is SSM is 0, SSOE is 1, which is also in CR1, I think, if I'm not wrong. It could be in CR2. Why can I not see that bit? SSOE. Where is the SSOE bit? Oh, it's in CR2. Correction. So it's going to be here somewhere. SSOE bit, yes. This one. So what does this mean? SSM is 1, SSOE bit is SSM is 0, SSOE is 1. This is used when the device operates in master mode. The NSS signal is driven low when the master starts communication and is kept low until SPI is disabled. Cool. NSS output disabled. So SSM is 0, SSOE is 0. This configuration allows multi-master capabilities for devices operating in master mode. So basically, you could have more than one master connected to the same peripheral. And basically, SSOE 0 and SSM 0 says to the master, hey, there might be another master, and right now it's not you. If that. So, and that means there's another master talking, and right now it's not here. Okay. Any questions? Quite quiet in here, but I'm happy. Cool. So almost an hour in, we're almost finishing the functional description, almost getting to the code. So types of configurations. How can we? Okay, cool. So let's go through all the bits, and then we'll look at types of configurations, and then we'll kind of come back and write the code. So clock phase and clock polarity. This one's a simple, really. Um, Clock polarity is like, hey, my clock, if clock polarity is 1, it means your clock is biased high when you're not communicating. So your clock signal is 1 when you're not communicating. That's clock polarity. And clock or clock polarity is, does your clock stay high when you're not communicating, or does it stay 0? Does it stay low? Staying high when you're not communicating is when you set it to 1, and staying low when you're not communicating is when you set it to 0. So that means when SPI is not talking, like the clock is just a constant either high or a constant low. So you set that with polarity. This you will mostly encounter from the datasheet of the peripheral you're going to connect. It will want you to have some certain clock polarity so that it can divide, it can cooperate, and you'll have to follow that from there. Clock phase is that when you clock phase means like when you start communicate, when do you want the data sampling to start? Is it on the fast edge of the clock? So fast edge, I'm assuming let's just assume you have a clock polarity of high. So your clock is high. So if your phasing is 1, it means you will start at the second edge of the clock. So if it's high, it will go high and then it'll go low and then it'll stay low and then it'll go high again. When it goes high again, that's when data sampling, that shifting of bits, will start. This is if your clock phase setting is 1. If your clock phase setting is 0, it means the moment the clock changes from whatever polarity it is, high or low, that edge is the one you're using. So the easy one is to think about phase 1 is the second edge, phase 0 is the first edge. Or you can interchange them if it's easier to understand that way. Okay, let's look at other bits. Data frame format. So when you're shifting data, you can either shift beginning with the most significant bit, or you can shift beginning with the lowest significant bit or least significant bit. So this is the LSB fast or LSB fast or LSB, so the LSB fast register, this one, I think it's in CR2, LSB fast, come on, or CR1, yeah, CR1. This is when it's 1, you're sending the lowest significant bit fast. When it's not 1, you're sending the highest significant bit fast. Okay, cool. So that's number 1. And then you've got 2 options. You can send data in 2 types of packets, an 8-bit packet or a 16-bit packet. A 16-bit packet has 16 bits, an 8-bit packet has 8 bits. And in order to change which one you're using of this is you can use the CR1 register called, or maybe CR2. CR1 register has a bit called DFF, and you can set that. So I think if you set that bit, if that bit is, I don't know, I don't remember. Yeah, that's a bit that you use to choose. So you can, that's number 1. That's, I think, most of the control bits. We've kind of gone through them all, but ask any questions. Check the charts. No questions. Quite quiet. Check the WhatsApp. No questions. Cool. Next. Okay, cool. So there's two options. Whenever you're using SPI for communication, you can configure the device as a slave, or you can configure the device as a master. And a master is a controller or the main or a server. A slave is a subscriber or the client, whichever words you want to use. So procedure, what you need to do, you need to set when you're doing it as a slave, you need to set the data bit for the data frame format, choose 8 or 16, set the polarity and the phases that we've talked about. Set the frame format. Are you doing MSB fast or LSB fast? So, and when if you're in hardware mode, the NSS pin must be driven low. I can't say NSS. Yeah? And then if maybe the device you're using, the device you're controlling is kind of switching between master and slave, so you need to go back and reset it. It could be a master and then it finishes communication and goes back into slave mode. So you need to set it so that it becomes a slave, and then you just load data into the TX buffer and start sending. And loading data into the TX buffer is probably, you'll have a register you can just write into. It's not like something you have to go and do. I'm now realizing that there's a lot of stuff in the language of embedded programming that basically you have to understand, like buffers and registers and stuff of the sort. If anyone wants me to do a thing on that, we can actually do a thing on that and let me know. Comments or WhatsApp. Okay, cool. So transmit sequence, you write into the TX buffer during a write cycle, and transmission, when it goes like the transmit sequence begins, is like from here it's almost electrical and it's lower than what we're covering right now. So it's FPGA stuff. You don't need to do this. This is done for you. You will write into some sort of register or some memory location, and this will kick it in for you. And so everything is loaded into the shift register, the TXE flag, which is TXE in operation flag in SPI SR status register is set. And on the transfer of data from the TX buffer to the shift register, and an interrupt is generated if the TXEIE bit on the SPRs. I think TXEIE is there's an error. So if an error occurs, you'll get an interrupt. If the transfer occurs, you'll get an interrupt. Now, being a receiver, to be a receiver, we're quickly getting on an hour. I think today the thing I will do is I'll finish all the kind of functional description. I could do the structs as well, actually, to be honest. So we'll see. We could do the beginning struct and then we'll leave it at that. And maybe the header file. So receive the sequence, receiving sequence. This is basically you're just waiting and data comes to you. And if your NSS is pulled low, you will receive the data. Cool. So that's it. Configuring in master mode, you have to define the baud rate, so the speed. You have to select your polarity and your phasing. You have to select your data frame format. You have to configure which LSB or MSB fast. You must set the master and SPE bits. Basically, you're setting yourself as master, and then you write into the TX buffer. And basically, for receiver, it's the moment you get data. So, and then SPI has a number of types of configuration. You can configure it as half duplex, a full duplex. Full duplex is master and slave transmitting data at the same time. So the master is sending from the slave to the slave, and the slave is sending to the master at the same time. You know what full duplex? I assume people know what full duplex means. Half duplex means it's either a write-only system. Think about a system where like the master is MCU and the slave is say screen. You'll never read from the screen because no one can, unless it's a touch screen. If it's a touch screen, that's a different story. But if it's not a touch screen, you're not going to read from the screen. So there's only one line of communication. Basically, master writes to the screen. Cool. And then if that's for simplex, half duplex is one way. Yeah. Simplex is half duplex, but it's basically it's held to that. Half duplex could be, oh, when the master speaks, the slave doesn't speak. That's a half duplex system. A simplex is a receive only or a transmit only system. So there's like I only send data or I only receive data system. So that's a simplex system. So there's three types: full duplex, half duplex, simplex communication. Okay, cool. So okay, cool. This is all in the datasheet. We can go further into this. We've done slave management. We've done polarity and phasing, uh, clock frequency. We spoke about that, but not really. So data, data. So the speed of sending data, this, boom, 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 boom. In SPI depends on how fast your clock. So every clock cycle. So when when you're setting up, you have a pre-scaler. So in your registers, in your CR1 or CR2 registers, you'll have a pre-scaler, baud rate 1 and baud rate 2 and baud rate 0. So this is a pre-scaler, this 3 bits. And you can use this 3 bits to set how fast your communication is. So basically you can get a clock from somewhere, either divide it. I think the least you can divide it by is 2. So you'll have to divide it by something. You won't be able to just use your full clock. And this is for STM32 devices at the moment. There could be an STM32 device that does not need this. So once you do that, you will end up in a place where you have everything set up, you have the speed set up, and what you need to do is now just start sending data. And how you do that is covered in either start sequence in master mode or start sequence in slave mode, and how to handle and transfer data. I'm not going to talk about how this works because it's easier when we just do it, and that will be easier in the code. So I think I'm going to take the next maybe 10-15 minutes. A lot of embedded code or embedded programming is mostly, if I can explain it, is mostly reading documents and setting the amount of code you have to do is very it's very little compared to how much, say, I would say how much reading you have to do. You have to read a lot and you have to find out a lot, but you don't have to, the code is not a lot. It's more, it, at this layer, it's a lot about understanding what needs to happen and then doing it. And the doing part is quite little, but the understanding part is a lot. As you can see, we take an hour to talk about it, and I'm going to probably take 10 minutes now, or maybe even 5 minutes. And in the 5 minutes, I'm going to just punch out some code to build, I think, to show you how we take this information that we've absorbed now into now into code into now. You've read all of this, you've read the data, we've read all the data sheet. How do we make it so that it's how do we all of the stuff we've just now consumed, how do we make this into code? That's what we're gonna do now, make it into code. So the code starts here. Cool. I'm writing my code on an STM32 IDE, STM32 Cube IDE for today. You can use Kyle, you can use not an IDE, depends on what you want to use. That's all quite easy. Okay, cool. So here's the first thing. We're going to the project. I'll share the links. The links to this project and everything will be in the description. You should have it already if you're on this stream. I don't know how you got to this stream without the link to this project, but should be in the description. Or rather, I can actually just quickly, what I can do is quickly just GitHub, Zach, STM32F1 drivers. So this drivers, okay, cool. We'll make issues, ask for questions on this thing as much as you can. It'll be really helpful for me. Cool. Awesome. That's where this project is, and I'm gonna quickly now write some code. So the first thing I want to do, the first thing I want to do is I would like to build a struct, a definition, a registered definition for SPI. Okay. Basically, this is add all the yeah, no, not that. Add all the SPI things that we know. It's slow because I'm streaming and writing code at the same time. So basically, our document has described a few things to us. All these have been described to us. Okay, uh, all these registers have been described to us. So these registers have been described to us, and now what we want to do. Now, what we want to do is we want to add all these registers into our code so that we can actually use them. Does that make any sense? We want to add all these registers into our code so that we can actually use them when we now need to, I'm thinking, in order to do the functional description. So we need to add these registers to our code. This is going to be hard. I need to understand exactly what I'm doing in order to explain, which is good, which is cool, very cool. So let's go. That was EXTI, that was GPIO, config, EXTI, FIO. So let's go here and let's make an SPI register definition. Does that explain itself? SPI register. So basically, this is the registers that we are going to use when dealing with SPI. So let's make a register definition, a struct, and make all of these volatile, int 32, T. Let's go T. Okay. C R R1. I wanna, before I go on with this, I just want to make sure I'm doing the right thing. SPI control register 1, the 0 offset, or 4. Yeah, it's basically the way they're ordered here. Cool. So let's add all of these 32-bit registers. This CR1, CR1. Okay. What's the next one? CR2. So I'm just gonna copy this. CR2. And I'm able to follow their organization because I can see their address here. That's the one that follows next. We'll talk about, you can ask questions about this. Um, it's not very difficult to understand, but I'm pretty sure, like, if you've never seen this code before or code like this before, it doesn't make any sense. I feel like I'm the only one who's never seen code like this before. So, and then there's the data register. So we can actually define this as we go along. So status register tells you the status. Data register, this is data that is received or sent. Cool. So DR. Okay, cool. And then I think CRC, PR. So this is, we use this when we are doing, if you need, let's look at it. CRC polynomial register. This is used for, like, if you want to do CRC checks. Basically, do you want to make sure that your data, the data you received is the data that was sent. Check some correction. Check some result. Checking. Whatever. We'll figure it out later. That might come. That might become a thing. Don't worry about doing it. Um, you basically, it's done in hardware. Maybe, maybe I'm not. Maybe I'm actually not like being truthful, but I think it's done in hardware. But okay, TX CRC R. Okay, cool. And then what's the next one? Do I need to add the I2S? TX CRC R I2S CFGR. Oof, that's good. So this is later. We might want to use this protocol. Might as well cover it for correctness. Oh no. So this is uh, so I2C, I2S, I2SS, CFGR. Yeah, you can come in. Busy in the game. Say hi. Okay, cool. Cool. My wife's looking for me. I think I need to go do something else. I spent too much of my time coding. PR. Okay, cool. So let's look at the definitions of those both of them. So this is configuration for I squared C. We're not I squared S. We're not using that. And then this is a prescaler register for I squared S. We're not using that for now. Cool. Here's the register map, and that's why we could define everything following each other as 32-bit integers. As you see, everything is a 32, 31, 32, 31 to 0. Boom, that's done. So the other thing we need to do, the other thing we actually need to do is add, we need to add, um, mm, 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 mm. I'm just looking at some code I've written before that's going to help me with this. Sorry. Are you that kind of coder who do you look at uh, do you look at code you've written before so that you can see what you've written? I wonder. Yeah. And I hope my audio is like good because audio. Okay, cool. So that's the first thing. And then the next thing we need to do is do SPI base addresses. So let's see. Oh, there's SPI1, SPI2, SPI3. Oh, okay, cool. So the base addresses are there. So what we, the base address is what points us to this. The base address points us to here. SPI registers. So the base address sends us here. So if we can make an S, because our controller has more than one SPI unit places. It has three actually. So the base address will send us here to both three. So we need to define those so that when we're using SPI, we can actually push them to the right. We need to push them to the right. How do we say this? SPI one base address. I'm confused. So that when we are coding, we actually use the right peripheral. Yeah, that is actually it. So that when we are coding, we can actually use the right peripheral. So let's add SPI1, SPI2, SPI3 here. So hash define SPI1, hash define SPI2, hash define SPI3, 3, SPI3. Cool. Perfect. Now let's make it so that they can send each other to, they can actually get each other. So the first one would be SPI reg 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 def g, and then SPI1 base. It's just weird to write code in. I'm usually not writing code in this size of text, if that makes sense to anyone. And this is going to be SPI2, and this is going to be SPI3. Perfect. So now we have all the SPI SPIs. Now we have all the SPI peripherals defined. Okay. So now what we want to do is we want to go and find the IRQ numbers. So this interrupt request numbers for SPI. There's a table here. Yeah. So here we wanna put this SPI1, SPI2, and I think there's an SPI3 somewhere. So let's define this. Later we'll use them. Ooh, ooh. Yeah, it's the same thing. It's the same thing. It's the same. Probably an SPI3 somewhere. 51. Cool. So let's quickly do that. Define those three IRQ numbers. We're going to use them later. We'll learn about this. We will learn about this. Boom, boom. Okay, cool. So that's okay. Let's build the code. Hopefully it works. Build project. Shame. $153. Nice. That's because we haven't named this struct. So this is SPI reg. That's why the auto completion did not work. And let's build that again. Okay, so basically all the I need to start item. All the registers that we were talking about that we're gonna use to control SPI, we've basically defined them. If that makes any sense, I'll just add a cd documents st workspace target my workspace target STM git status git check out SPI 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 work. Yeah, it's gonna be a big one. So I'm just checking out a new branch so I can commit this work. I get status, I get drive, commit, and define all the SPI registers we are going to use. Okay, and then in addition to this, I'm just gonna make 2 more files, and we're gonna stop at there. We're gonna make we're going to make an SPI header file. So let's go back to our code in here. In here, drivers, since it's drivers we're building, let's make an SPI header file. New file. New header file. It's STM32F1xx underscore SPI.h. And then in source, we're gonna make, oh, I will rename this. This is 103xx. Okay, cool. And then in here, we'll make a new file, new source file, STM32F103xx SPI. Okay, awesome. It status drivers. I'll just check for questions just now. Drivers. Add a header file and a source file for SPI. Git push. And we'll finally go to our browser here, and we should have a new pull request open. SPI work, prepare pull request. Completes this try this PR attempt at doing the work, define find in hash. Okay, cool. Hash 5. We'll define the bigger stuff and later. Cool. So there we go. We, as a quick recap, we discussed what SPI was, how SPI works in STM32 devices, what registers and watch controllers we need to use when configuring SPI. And we basically transformed all the speaking that we had into code by defining the registers that we needed to use, the register definition struct. We added some IRQ numbers so that we can actually handle interrupts later when they come. And we added a SPI header file. And I believe, I don't know why. I have no idea why. Git status. Something's wrong. Oh no, this, whatever this is, deleted. Okay, so it's here in source. New source file. I chose source folder STM32F1xx underscore SPI.c. Cool. Status. Okay, perfect. That is 1.5 hours of talking and making files, and I think this is it for today. So if you want to push that, feel free to leave any questions on the code. Feel free to add any issues to the code. Feel free to send me requests and stuff of what you think we want to possibly work on in the future. But from here on, see you. I'll announce another stream, maybe another one this week, and we can work on actually setting up SPI on the STM32. One final check for questions, none here. And I will gladly say thank you so much. And